Hi, my name is Roman Gallegos, and today I'm going to talk about the photovoltaic system design in Guayaquil, specifically in Malecón 2000. We are using PVsysTM 6.2 software. This is the subject renewable energy. Um, and today talk about sign of conductor and protection for string boxes. There are 24 strings in parallel. If I one string box for each artboard, each artboard must contain the parallel strings over number of inverter inputs. This is equal to 24 over 3 equal 8 parallel strings. Each of the chains has 28 panels, so there will be 144 panels per workbench. This is very large and impractical if you place two chains of panels of each workbench. With a secondary string box, you will have 4 artboards with secondary string box indicated the illustration. I can see in this illustration is repeated 3 times for connecting inverted inputs to 3. The word table also 2 vertical and 18 horizontal panel connected, and the secondary string box will have a fuse for each string or parallel panels, a main circuit breaker for each of the parallel panels, and main circuit breaker for each one. The fuse current is a 10 ampere in CD. And circuit breaker we have multiplication 7.92 times 2 equal 14.184 amperes, approximated 20 amperes in DC. For the primary string boxes, there are only 3. We also have a fuse and main circuit breaker. A fuse is equal to 20 amperes in DC. It should be considered that with a protection factor of the 1.25, there is a 98 amperes, in addition to a fuse for each circuit. There are 4 secondary string boxes connected, so there are 4 fuses, one for each circuit. And circuit breaker for this is 18 ampere in DC. This is a circuit breaker for each main string box, considering that the protection are in DC. Finally, for this project, 12 word tables are needed, with 2 strings in parallel, 3 main string boxes. One for every 4 secondary strings are there connected to the 3 DC inputs of the inverter. About transformer capacity, we have a turn radio. For this, we have a data about inverted DC and B nominal and E max. For this we have a power the 100 kilovolts ampere. Thank you.
Hello, my name is Samantha Sanchez, and today I'm going to talk about the unifilar diagram. First, as my partner mentioned earlier, the protections for the circuit are arranged as follows. First, we have the 10 amp fuses for each work table along with its respective 4-pole 20 amps breaker. Then we have the 20 amp fuses for each secondary string box and 2-pole 80 amps breakers for each primary string box. Here. Now, the conductor to be used will be the concentric type of PV wire for the positive and negative cable, only for the DC circuit, that is before the inverter, meaning all of this. Now, for the conductors from the work table to the secondary string box, it will be used cable number 14-7 wires from each work table. There are 4 cables, 2 positives and 2 negatives, 1 for each string to each fuse. Now, for the conductors from the string box to the secondary string box to the primary string box, it will be used cable number 14-7 wires. 1 positive and 1 negative cable will come out of each secondary string box. And finally, from each primary string box to the inverter, it will be used 2 cables number 7 wires. 19 wires, 1 positive and 1 negative. Thank you.
Installation clips. The place of the installation is between Rocafuerte and Simon Bolivar, better known as the Malecón. As can be seen in the presentation, we have the latitude, length, and time sent values. Well, photovoltaic panel dimension. The panel have the following dimension for length, width, and thickness. So it's important to know that the number of the cells is presented both in series and parallel for the design. For example, in the same way, we have the electrical data of the panel, such as short circuit current, maximum power point, and open circuit current, and marker. So if the marker is zero energy, the maximum power point is approximately 7,900 ampere, but it's so important that design this condition. So in the dimensions and electrical data of the inverter, it's important to know that the width, depth, height, and weight. So consider is the way same that the electrical data of the short circuit, voltage MPP nominal, voltage MPP maximum and minimum. So we have the dimension of the inverter is width, depth, height, and weight. In the width, it's approximately 1,218 millimeters and considers various parameters.
My name is Michael Orella. I will explain the result obtained from the photovoltaic system without shower in the area Guayaquil Malecón. We established geological characteristics to us and azimuth 10 grades in the photovoltaic system. The number of the units 432 panels have the 424 watts because the total power of the 104 kilowatts because the inverter with the capacity of the 100 kilowatt and C8, and be not having loss in the photovoltaic set rangers, and the losses of the 1.5%, and the characteristic is photovoltaic systems and um, photovoltaic photovoltaic panels and inversors and characteristic electric. The red bar represents use the energy produced at the output. The inverter with an amount 144.3 MD watt for years, and the table represents the balance of the mode of the consumption, of the photovoltaic, the assembly, and the graphic systems mounting irradiations of the 0.99 kilowatt meter per days, and the curves represent of the average incidence and the solar 80, the azimuth and the irradiation per day of the photovoltaic per days, and the figure is the model photovoltaic systems without shuttle in area and Guayaquil Malecón. Thank you.
Good morning, my name is Brian Cisalema. Today we are going to do a project in PVsysTM, considering the effect of the buildings near of our project. Now we put in this option, sondeados cercanos, and then we put construction perspective is a work in 3D, is a map. Now we put the buildings that are near. In this case, we consider that the building that in the south, in the north, and in the west. We don't consider the trees in the east side because they are a little far. We don't consider that because the Malecón Avenue is big. We don't consider that the effect of shadow makes something in our performance in our project. We have 12 tables with a distribution of 36 panels, put 18 in series and 24 in parallel. We make groups of four tables of work because we have this converted. This is the junction box, and we consider 4 by 4 because our converter have this limitation. Then we're going to work with this. Now we're going to do the simulation how the sun gonna move along of the year. We can see the variation of the shadows over the project, and we can take the performance of our project considering that. Before we are going to take how the sun make the move along of the year. We have a graphic that shows how the performance goes down. Consider that you don't have buildings near. We're going to compare it now. Okay. Now we have the results. We we can see that we have a production of 116 megawatts hour per year, and we have a specific production of 1,118 kilowatts hour per year, and performance of 74.6%. This is considering the shadow of the buildings that are near our project. If we don't consider that, we have the next results. We have 124.3 megawatts per year and a specific production of 1,199 kilowatts hour. That's peak. And we have a performance ratio of 80.2%. We can see in that simulation that we have a little bit low the performance considering the effect of the buildings. But according to this, we make analysis of the invest in the project. We can check that it is possible to make that the performance goes up, but this improve gonna make a little the prices goes up, but we have to do an economic analysis. This is all. Thanks.
Hi, my name is Tyron. I'm going to talk about problems identified in the system. Problem one is that building near our installation gonna generate shadow over the PV panels. So we need to find the best position and the height to receive the more energy possible. The second problem identifying the system is that because the sun comes from the from west and goes from the east. Come from the east and go to the west. There's going to be a time where the building that is next to our installation will produce shadow. It's going to be like 4 p.m. So at 4 p.m. we won't receive sun energy. So we need to solve this problem. Thank you.
Greetings, teacher. I'm Luis Pesantes, and I'm going to talk about the proposed solutions. As already mentioned, of the main drawbacks is the problem of shadow generated by the buildings surrounding the photovoltaic plant. And these shades bring us as the main consequence problem the reduction of energy production. The shadows impact directly on the power that will be expected to obtain from the solar panel. Possible solutions and the internal connection of the solar panels. When panels are connected in series, the loss due to the shading can be 50%, while the losses when panels are connected in parallel can be up to 90%. It is clear then that it will be advisable to have a series connections to mitigate this problem in this part. Well, other solutions can be the orientation of the panels. As shown in the figure, to reduce this effect, you can change the orientation of the panels, making them coincidence with the path of the sun to optimize as much as possible the energy generated. Well, if the problem of shading is extreme, a solution will be to find a new area where to collocate the plant. If possible and technical and economically feasible, could be placed on the terraces of buildings, as shown in this figure.